Okay, good morning all of you. My screen is visible. Anybody?
Yes, sir.
Okay. So we'll see that switched mode power converters. So normally, why we go for all these things? As you are aware that the load is DC. Let assume that this one is a DC load. You may have as a DC supply. Now you cannot connect directly like this. The reason is suppose load voltage may be something, battery voltage may be something. So it will not be possible direct connection between the source and load. So that's what the difference actually. We can see that load voltage may be 10 volts we may be required, and then battery voltage is a 230 or 210 or a 50 volts, something like anything different. And that's the reason directly source and load is not possible to connect. That's what I give an example also here. Battery may be 12 volts or 24 volts or 48 volts battery, but load may be 5 volts. Then direct contact is not possible. That is the case. What we want to do is we have to create one interface. This is the interface. So the load may be 5 volts may be required, and source may be something else. Then there is a DC to DC converter is required to control the voltage. So whatever input voltage is there, you have to control that, and you have to pass the output voltage is suitable to that of a load voltage. So that's what that is the case. But some cases input may not be DC directly, may not be as a battery, it may be AC also. Then what you have to do, directly AC cannot connect it to the DC to DC converter. Then what else you have to do, you have to convert that AC to DC by make use of the rectifier, and then use the filter for filter out the harmonics and ripple and all, minimize the ripple quantity. Then only you have to connect as a DC to DC converter. So like that. So for that I used this circuit. Now you can see if AC is available, then you have to convert that AC into DC using as a diode rectifier, and after that you have to use the filter to filter out this ripple quantities, and little bit will get it as in the straight line in fashion. Then you have to use as a DC to DC converter. The DC to DC converter may be anything, or let you can see that as you are aware that previously there is a switch, then diode and inductor and capacitor. So all these things, this circuit may be buck chopper or a boost chopper or a buck boost chopper, or else you can say that step up, step down, up and down. So all these things, anything depends on our requirement. You have to use this DC to DC converter to connect it to the load. So that's the actual thing. Now how this DC to DC converter will operate. Now we can see that earlier, if these things switched mode is not used, there is a linear regulators also available. What is the linear regulator? This is a one of control. If DC is available, variable DCs will be obtained using linear regulator. So the linear regulator are most powerful until the advancement of SMPS switched mode power supplies. Before that, we are using as a linear regulator. So it is very accurate and precise and very good regulation, but the drawback is there, it is not efficient. Why it is not efficient? Because the linear regulator will be used as a resistors. So that resistor is nothing but a power dissipation is taking place. That's why efficiency of this linear regulator will be poor. Other than that, it is very effectively controlled, and they are using also. Now the switched mode regulators are more efficient because we don't have any loss components. We are using inductor, the capacitor, and then switch. That switch is ideal switch. Losses are very negligible, or it may be MOSFET or BJT or IGBT, anything. Semiconductor switches are there. So that is the reason switched mode regulators are very efficient. It is nearly 100%, 99.89, like that. We'll get it as a efficiency of these regulators. That's why this is very popular nowadays rather than the linear regulators. We will see that how the linear regulator will work. Let's consider there is a rheostat in between this. So load is something, we require the voltage, source may be something else. Then make use of this rheostat. We are controlling the voltage or nothing else. We are drop that voltage here. The rest of the voltage is connected to the load. That's what I mentioned here. For example, 48 volts at the input. Now the output I need only 5 volts. Then what is required? 43 volts has to be drop across this resistance. So that is the linear regulator case. And this will be, you can see that series drop resistance. And then almost all the linear regulator will use this concept. But what is the problem? Once the current is passing through this resistance, automatically I square R loss will be takes place. That is the major drop across that resistance. I square R loss is a power dissipation. Our intention is not power dissipation. Our intention is a variation of the voltage. But during the variation of the voltage, it takes place is a lot of power dissipation. How to overcome the dissipation? So by seeing this, you can see that I square R is the loss. But now I don't want to make this something, you have to make it as a 0. Anybody, how will you do that? I square R loss is equal to 0. Two options are there. So one option is, if current is 0, it will be 0 because I square R into, this one is 0 into RS will give you the 0. Or another way, there is RS also, you make it to 0. How to do that? Instead of using this resistance, this approach I required, either current has to make it to 0 or resistance has to be 0. If any one you make it to 0, then automatically resultant will be 0. Then you can see that suppose if I use as a switch here, instead of resistor, if I use switch here, if the switch is open, then what will happen? Switch is open in the sense what? No current pass through that. Current is 0, means resistance is infinite. Then what will happen? The power loss will be 0. And switch is closed. Then what will happen? Switch is closed means then this will be short circuited. Across that the resistance will be 0. Then automatically power dissipation will be 0. So this is the mechanism coming from here. The approach is like this. Instead of getting I square R loss something that is a power dissipation, to overcome the drawback, what they thought is they replace the resistance by a switch, controllable switch. If you close this switch or if you open this switch at any instant, you are getting I square R loss is a 0. So that is only the logic here. We can use that is our chopper case. So I square R loss must be 0. Either you make it resistance is 0 or you make it current is 0. Current is 0 in the sense R is infinite, no? So it won't allow. That bit switch will be open. So like this, we can able to control our voltage, but power dissipation will be 0. That's what I mentioned here. When I is equal to 0, the switch is open circuit. And switch is open circuit, the current through this are 0 and also power dissipation is 0. Or other version also I mentioned, no, if RS is infinity. When RS is infinity, only two conditions. One is not dissipating the power when RS is 0 or RS is infinity. That means RS is infinity in the sense current is 0. So in that we can able to. So to achieve this, whatever I explained here, to achieve this process, what we required is we have to replace that resistance by a pole or a switch. Simply, if you do that, we can get it. Now we will see that is what linear regulator is going to come into the picture. Instead of resistance, we are using as a switch. We can control that way. And other version, you can see that how the inside switched mode converters is going to be operate. We will discuss something introduction to the switched mode regulator. So this will be widely used in the regulating the power That's what you can use as a DC motors application, and only in PCs also they are using. And now input of these converters in unregulated DC voltage, which is obtained by rectifying a line voltage. How I mentioned one of the diagram. No, if input is AC, then what I have to do? After getting AC, you have to convert it into diode rectifier. If diode rectifier, if you use, we'll get it as a DC. So that instead of directly using as a battery source, if it is available, you can use it. But most of the cases, input is a AC supply. That's why we have to use as a diode rectifier. By rectifying the line voltages, we are getting as a DC. But now here you can see that what will happen if this supply is fluctuate. If supply is fluctuate, this also will fluctuate, then that will affect the voltage magnitude. So that's what you can see that fluctuate due to the change in the line voltage magnitude. If the line voltage is fluctuating, automatically output also going to be fluctuate. And this switched mode DC to DC converters are used to control the unregulated input into the control the output voltage. So that means whatever may be the input, our desired voltage must be, that is what the switched mode converter, this must be maintained constant. Whatever voltage you need in the load side, in the load side voltage is 5 volts, even input may be 220 volts or 230 volts or 10 volts or whatever may be the input voltage, you need to maintain output voltage must be constant. That is also one of the way. By varying the input also you have to maintain constant output voltage, or else by fixing this input maybe 10 volts, you need to get output must be variable one. This also is possible. Like this, some of the options are available to get it as a variable output voltage or a fixed output voltage. Now for that we are using as a buck converter or a regulator, both are same. Buck regulators, boost regulators and buck boost regulators. So using this we are able to get that our desired output voltage. Normally basic choppers are these two only, buck and boost. By combining this analysis, buck and boost will be formed. Only thing is components we are interchanging. So this is the three. We will see all the three one by one. Now internal structure of the switched mode converter, as I explained previously, there is a input AC supply, then use a diode rectifier, it will get it as a DC. This DC is not a controllable one, that must be remembered, because we used here is a diode rectifier. Diode rectifier, it will convert AC to fixed DC. That's why we are not say this voltage is a variable voltage, that is unregulated voltage. Now we can see you are using as a filter, filter out this harmonics and all, and still after filter also it is unregulated. Now you make use of this DC to DC converter. This DC to DC converter, any of our depends on our requirement. This may be buck converter, or maybe boost converter, or maybe buck and boost converter. So these are the things we need to use. And once if I use this is our control parameter. By controlling this, we are able to control the DC regulator output voltage that is connected to the load. Depends on our load requirement. Some loads may require as a constant voltage, irrespective of the input fluctuations. You may be need constant voltage. Some applications, even though input is constant, I need variable voltage. Suppose if I use as a motor, what will happen? Once if I use motor, then automatically there is a variable voltage is required. So if I use motor variable voltage, I will get again this phenomena. By controlling the SMPS, that is either buck or a boost or buck boost, depends upon our requirement of the load, you can able to control the output voltage. So this is the basic block diagram of a switched mode converter. Now that's what I know. Out of all the three, there is a step down and step up are the basic converters, and then buck boost is a combination of the two basic converters that we'll analyze that. Converters are analyzed in steady state mode only. The switches are treated as a ideal switches. These are some of the assumptions. Anyhow, I will show that assumptions same thing in the later slides also. Switched mode, once if you use as a switch, that loss will be minimum. So that means it treated as a ideal switches. And losses in inductor and capacitors are neglected for analysis purpose. And DC to DC converter, average DC output voltage must be controllable one. So equal to desired level. So whatever average, once if you are operating as a switch, whether you are turn on and turn off all the choppers, whatever chopper you want to use, while you are using that, our intention is only turn on and turn off. And switch mode DC to DC converter utilize one or more switches to transform DC from one level to another level. So that is also because we maybe use diode, one of the switch, and there is a BJT or a MOSFET or IGBT that is also on of the switch. Like that, you maybe use a more number of switches also to get our desired output voltage. And the input voltage, the average output voltage controlled by controlling the on and off. That is only total switching action of the power electronics. So I want to control the output voltage only by doing the switch it on some duration, switch is off some duration, whether it may be chopper or maybe rectifier or a cyclic converter or an inverter, wherever, or any controller you can use it in maybe any application. Our intention is to control the output voltage by means of on and off. So that's what a simple example you can show that as you know that buck chopper or a step down chopper. Now you can see there is a DC and switch. This switch may be anything, and I have to give the firing pulse to this to fire this, and then diode, and then inductor, capacitor for constant voltage purpose. Now we can see that here I want this much voltage. You can do the simulation also the same thing. I want desired voltage. Let assume that I want 6 volts or 10 volts or 15 volts, whatever may be. Depends on our requirement. Now the system is operating. This voltage may be more or less. Let it be this voltage is something 5 volts. Let assume that. Now our requirement voltage may be 10 volts, but it is running under 5 volts, getting in the 5 volts. Now what I have to do, I am sensing that voltage. There is a sensor. We are sensing the actual voltage, and then we are giving to the error amplifier. What it will do? Actual voltage is 5, required voltage is 10. Then the error is passing through the PI controller. So PI controller is going to nullify that error. And now we are using as one sawtooth waveform to compare. This is a comparator. So this one is error amplifier, and then PI controller and comparator. So what the comparator will do, this error signal and then sawtooth signal will compare and will generate as a firing pulse. Here instead of pulse, we can say that duty ratio, that is a T on by T. Whether we want to provide the firing pulse or you have to disconnect the firing pulse depends upon our requirement of the voltage. The desired voltage is 10. Available voltage is 5. Now you provide the firing pulse. If I provide pulse means here is a duty ratio. So on period. So firing pulse will be given to the switch. Then switch will be on. Then what will happen if switch is on? Then automatically this voltage will be rises gradually. Once this voltage and this voltage is matches, the error will be 0, and then the pulse is going to be running continuously. Once if it is high, let it be our intention maybe 6 volts, but it is already reaches 10 volts, then the otherwise version is going to be takes place, and disconnect the firing pulse some duration, and it is gradually drop down. So like that, always all the things is going to be happen inside this control circuit, and finally you will get it as a constant desired voltage. Whatever you decide here, requirement voltage if we provide simply, then automatically within a fraction of seconds it will reach as a desired voltage. That's what you can do the simulation also. Same thing, whatever I explained, I did a simulation. I given as the input is a 14 volts, and then switch is used MOSFET, then the diode, and then there is an inductor, this one capacitor, and some load. What I want is, I want the output voltage must be something desired voltage. Let it be desired voltage I want as a 6 volts. See, I given this is a constant. You just connect one constant 6 volt. Later you want to make it 10 volts also, it will get 10 volt. Or you keep 20 volts also, it will get like that. So whatever based, but it is a step down chopper. So up to 14 only we are getting, and 6 I made it, it will get 6. If I keep 10, it will get 10 like that. So whatever change is made here, automatically it will be getting in the output side. Now comparator, there is a sawtooth generator, and the error amplifier input, one of the comparator input is this one, PI output, and then sawtooth signal, and these two will compare. Based on that it will generate as a firing pulse. And now you see the output, you can see that I made it as a 6 volts in the output, and it reaches as a 6 volts. This is the can see that this one is a 6 volts. Now it will take small time duration to reach as a 6 volts. Once it is reached 6 volts, it is continuously it is operating. And now you can see from here to here, very small time. How much time it taken? Only 0.3 seconds of time it reaches as a 6 volts. And once it reached, again if we change here, instead of 6 to 7, again it will changes to 7 volts like that. So you can do the simulation also using same circuit. Anyhow, I am sharing this now just for your practice purpose to understand. Now we can see the one by one buck chopper. What is buck chopper? Like a step down, no? A step down chopper only as usual. All the choppers, what you need is just to turn on the device and turn off the device. All the cases, switch is on, only 2 instants. You understand what will happen? Switch is on and switch is off. That's all. Switch is on, what will happen? Switch is off, what will happen? That's all. Based on that parameters, you are deriving the expression. Same expressions will get it. What is the output voltage with respect to duty ratio? See that switched mode, many of the books they use duty ratio D. Anything you can use it, no issue in that. Delta you want, you can use it. D you can use. Some books they represented alpha also, but alpha is not firing pulse. Here is a duty ratio like this. So any notation you can follow. And now I am using here as a D. Now we can see that switch is on. Let it be switch is MOSFET. If I close this switch, what will happen? What will happen? You can see that output voltage same as the source. It goes like this. This is the output voltage. So output is same as the source voltage Vs. If switch is on, then what is the voltage across the inductor? If switch is on, what is the voltage across the inductor? This side is Vs and output side is Vout. Then that is equal to VL. Vs minus Vout is equal to Vs minus Vout is equal to VL during on condition. As you know that duty ratio T on by T. So here total T is equal to T on plus T off. T off also I can write otherwise also. T off. What I can write? T minus T on. That is equal to T minus T on is what? According to this, T on is equal to D into Ts. Ts is a switching time. Or T. Any notation you can follow. Both are same. Some I use Ts. This is a switching time or switching frequency. Fs is a 1 by Ts. So now this into what I can write, T on is nothing but a D into T. Then you take common of T. Then what will happen? 1 minus T. So T off I can write 1 minus D into T. T on as usual T on, and then T on also you can write D into T. Both are same because our convenience given data we can able to use. Wherever T on is there, simply I will use D into T or Ts, anything are same, and T off is there, I can write 1 minus d into Ts. These are the two parameters I will make use later. Now, one is clear. When switch is closed, your output is same as the source. Inductor voltage is nothing but a Vs minus Vout. That's what I represented the waveform voltage across the inductor, and this is the output voltage, and then current waveform. This is a current waveform, and this is a source current waveform also. Now you can see when switch is off. When switch is off, what will happen? You can see inductor store energy here, and now the polarity is this is plus, this is minus. Then what will happen? This is open. So here is a switch is open. Now what will happen? Current will pass like this. Means prevailing diode is going to conduct. Prevailing diode is going to conduct, and then some current will flow through the capacitor also. And now we can see that when the switch is open, then the diode will be conducting, voltage will be 0. And what about the inductor voltage? I want when the switch is open, VL under off state. What will get it? Minus Vout, because this voltage and this voltage is same, only polarities are reversed, and this is plus, this is a minus while it is dissipation. This is in parallel with that we can say that it is a minus Vout. So when this, and current as usual, when the switch is on, current will be gradually rising, and this current is the switch current, S current or a chopper current, and this current is a dissipation current pass through the diode. Again switch is on, chopper will carry the current, and switch is off, diode will carry the current or dissipating the energy. And then what is the source waveform? Source, you can see that whenever switch is on, only you are drawn current from the source. That's why there is a, this current we call it as a source current. When the switch is off, what is the source current? 0 only. No, we don't receive any current from the source when switch is off state. That's why you make it as a 0 here. Only switch is on, you retrieve the current, and switch is off, can disconnect. That's all. Very simple. Just you draw the circuit, and waveform is simple. When the voltage waveform, inductor voltage waveform, output voltage waveform, current waveform. So now when the switch is closed, you will get Vs minus Vout across the inductor. Switch is open, only this voltage appear across the load, but sign polarities are different. That's why minus Vout. That's all. Now we will see the derivation part one by one. Before that, there is assumptions. I already mentioned in the previous slide also. What are the assumptions? Switches are ideal, no switching losses in the device, because ideal in the sense no resistance across that device. When the current is passing through that, it won't happen any drop. And now another one is a current through inductor is increases and decreases linearly. That is the another assumption. And then therefore what will happen? The rate of change of current, that is a di by dt, is a constant because it is linearly varies. And now the capacitor is large, then output voltage also constant. So let these are the some of the assumptions we made it. Now we can start as usual. And there is a buck converter, it consisting of a switch, diode, inductor, capacitor, all the load terminal, and then output voltage can be controlled from 0 to maximum. Why this will be statement? Because there is a buck converter. Buck converter is nothing but a step down. So output is always controllable only from 0 to VDC or VS or VD, whatever notation. So whatever input voltage you applied, whether if it is a 14 volts, means your output control only 0 to 14. It should not be beyond 14. That is the statement. The main application in DC power supplies. In our lab also regulated power supplies will be there. DC motor speed control. Input voltage source is connected to the controllable solid state device. So because of this switch only, you are able to control the output voltage. It may be used MOSFET, IGBT, but preferably we don't use thyristors. The reason is turn off the thyristor is a complicated. So that's why generally we don't use this type of. And also we are using as a filter to filter out that ripple and all harmonics. So for that we are using as a filters also. Now the analysis of the buck converter, you can see that very simple analysis. Try to understand this. Once if you understand this buck converter analysis, exactly same for boost and buck boost also. The reason is very simple. Same components only we are using. Only the different is instead of placing the inductor here, you may be placed somewhere here, and this diode may be somewhere here, or this switch may be somewhere here, like this. Only we are interchanging the component. That's why voltage across the inductor is going to be differ. Other components are same flow, will get it. Now as I told, there is a two things. One is a switch is on, another one is a switch is off. Now you can see that switch is on. What is the voltage across the inductor? My first question is, what is the voltage across the inductor? Now when the switch is on, we can see that voltage across the inductor is equal to input. Let's consider input is a VD, output is a Vout, then VD minus Vout, that is the voltage across the inductor. Then what is the current pass through the capacitor? So there is a IC. This is a current pass through the capacitor when switch is on. Now because the current is passing like this, no, automatically some of the current pass through the capacitor also. Then what is this current? That load inductor current. Whatever current is passing through inductor, that is IL, and then some of the current pass through the capacitor. So therefore I can write IL minus Iout is nothing but IC, because IL is equal to IC plus Iout. But I want IC no during on condition, that is equal to IL minus Iout. So like that. So these are the why I need these parameters. I want volt second balance equation, ampere second balance equation to get the derivation, current and voltage relations. For that I calculated voltage across the inductor when it is on, current pass through the capacitor when it is on. Same fashion you can see here, when the switch is open, this is open, then what is the voltage across the inductor? That when switch is open, voltage across the inductor is minus Vout. And same thing when the current pass through the capacitor, we can see that IL minus I0 only, because sudden changes it will not allow immediately, because the inductor is placed here. That's why again same current IL minus I0 only passing through the capacitor current. Now you apply the volt second balance equation, current second balance equation, or ampere second balance equation, volt second balance equation. What is the volt second means? During on condition, what is the voltage multiplied by time, plus during off condition, what is the voltage across the inductor multiplied by off time, that sum is equal to 0. So that is the volt second balance equation. Now as you know that during on condition, what is the voltage across that? VD minus Vout. What is the period? On period, no, on period is T on. How I can write T on? D into Ts, because D is equal to T on by Ts. S or T in both are same, no problem. And from this T on is equal to D into Ts. That's why I multiplied the on period plus what is the off period? When the switch is off, what is the voltage across the inductor? Minus V out. That's why I made it as a minus V out into off duration. So what is the off duration? That is equal to 1 minus D into Ts. This is already derived, because T on plus T off, that is equal to Ts. From this T off is equal to 1 minus D into Ts. So now that is equal to 0. If you simplify that equation, and you will get it, V out is equal to VDC into delta. As you noticed in the previous also, V out is equal to VDC into delta. Now same formula will arrive here. Now from this I can say that it is a step down chopper. Delta ratio is again same. From delta is nothing but a 0 to 1. No? Put 0, will get output 0. put 1, you will get VD. So input is equal to output if duty ratio is equal to 1. So controlling is 0 to VS or VD. That is only the controlling. Similarly, apply ampere second balance equation. Capacitor current during on condition plus capacitor current during off condition, that is equal to 0. So just same, we have that capacitor current during on, you can substitute here, during off also same, and this is multiplication of on period, this is a multiplication of off period. Now from this I got it, output current is equal to the inductor current, so that is equal to IL. Now let consider, this is the statement, input is equal to the output, let consider as a lossless system. Therefore input power is equal to output power. What is the input power? There is a VD is a input and ID is a current, input current, and VD ID, that is equal to output side V out into I out. These two are multiplied. You can multiply these two here. Then VD ID is equal to V out I out. From this we can get it as a ID, input current, is equal to D times of the I naught. What is the difference between these two? Anybody? V out is equal to VD into D. Here I input, this is input side, means current input is equal to D times of the output current, whereas voltage output is equal to D times of the input current. What is this relation? It seems to be as a transformer action. What is the transformer? In the our AC transformer, V2 by V1, that is equal to I1 by I2, that is equal to K. Same. Now we can see that V out by VD, that is equal to what I can write, ID by I out, that is equal to D. That means by seeing this relation, it acts as a DC transformer. See that relation between the output voltage and input voltage and current relations. Now D is a duty ratio, here also transformation ratio, and this is for AC transformer, this is for as a DC transformer. Now these are the some relations we got it from voltage and current. So V out is equal to VD into D and ID is equal to D into I naught. Now this is the one relation. Still we can see that capacitor and inductor design. Now when the inductor, how to calculate the inductor, value of inductor can be calculated based on the current ripple, delta IL, how much you are going to minimize with respect to the output, you can able to design the inductor value. Now for that, when the chopper is on condition, the slope of that, the chopper is on means what is the duration time, dTs, and the slope of the inductor, voltage across the inductor notation only. What is that voltage across the inductor? VL, that is equal to LdI by dt. What is di by dt? You can see that delta IL by delta t. So dt, what is the time duration? I can mention L into di, so I can write delta I by dt is TTS. So now what is the voltage across the inductor when the switch is on? That is already we know that VD minus V out by L. VD or Vs or Vin, anything is same, thus by L, because this L is coming like this, then that is equal to delta IL by dTs. That is one equation. See that, very simple. Voltage across the inductor, that is a VL, that is equal to L di by dt. Everybody knows this formula. What is voltage across the inductor when switch is on? V input minus output, that is the L. Di I can write DIL by T. Dt means time duration, that is a DTS, T on period. Therefore I can simplify this, Vi minus V out by L, because this L, that is equal to IL by DTS over. That is one. Similar fashion you consider for off duration. When switch is off, then what is that? Again same notation. Switch is off, what is voltage across the inductor? VL LdI by dt only. But what is this voltage? That is minus V out. L into delta I by what is time? Half time. T of I can write 1 minus D into Ts. So then divide by L here, minus V out by L, that is equal to delta I by 1 minus D into Ts. So both cases, second equation and first equation, both is having L. You just find what is the L over. That is the design of a inductor. Now I made it any one equation, you can take it, either this equation or this equation. Now I am simplifying this. Second equation or first equation, both are same. Now take it as a first one. Delta IL by dTs is equal to V in minus V out by L. From that L is equal to. So what I can write, L is equal to V in minus V out by dTs, this cross multiplication by delta I. So still you can simplify this. What will happen, this dTs, I will write denominator is a Fs, because they will give in the problem switching frequency. Switching frequency of a chopper is equal to suppose 10 kilohertz. Then automatically Fs is known to you. That's why ds I will write denominator, will get it as a Fs. Now what else? V out here. V out I replace by dt d into, because we know that V out is equal to delta times of Vd or delta times of Vs, both are same, or delta times of Vn, anything. So that is the output. So that's why I can write wherever V out is there, I will write d into Vin. And still you can simplify further, because here Vn is there, here Vn is there, I am taking Vn common, then 1 minus d into t, delta IL into Fs. So now we can simplify further. There is a d into Vn, I can write V out into 1 minus d. So why all these simplification depends on our requirement in the formula, because some cases they may give V out directly, some cases they may give d, some cases they may give switching frequency. All these parameter, based on the available parameter, you choose your formula. Anyhow, this is only the final. Just simplification I had done based on the availability of the parameters. That's why finally, what is the L value? We got it. L is equal to V out into 1 minus d by delta IL into Fs. This is the L value. So now based on the delta IL, this is the designer choice, how much you have to minimize the ripple. So that is the designer choice. They may say that 10% of the load current, preferably we will consider 10%. If you want to reduce further also, you just in the design parameter, whatever load current they may give, you take it as a delta is equal to 5% or 3% or 10%. You can substitute here. We will get it as a required L value. Now what is other one? Capacitor value. Because in a circuit we use it as inductor and capacitor, that is a design parameters. Now we can use here the capacitor value is calculated by applying ampere ohm second rule. Now you can see that this is the charging part and discharging part. That's what I mentioned here. Capacitor current in one period, sum of this will be the 0. Then 1/2 period if you take Ts by 2. This total ripple magnitude is a delta IL. So that's what I mentioned, from this peak to that peak. I call it as a this peak to this peak. This duration is a ripple, that is a delta is. That's what you can see, that Q is equal to CV, and one period if I take as a triangle, then we'll get it as a half into base into height. Then half, what is the base? You can see here Ts by 2, any one period, no? Ts by 2. And what is this height? We can make it as a total delta IL, no? But only this portion, triangle, we can consider that is a delta IL by 2. So now we'll get it as a what is the capacitor. That's all. So this is the value of a capacitor, and previous one is a inductor value. So that is the and further if you want to find other quantities also, you can see that ripple inductance value, because delta IL, if designer is taken as a 10% or something, you can find, take it. Otherwise also you can able to design the delta IL. So how will you get the delta IL? When the switch is on, inductor voltage is Vd minus V out, and inductor is LdI by dt, that is equal to this one, and delta I divided by on period is dTs. From that directly we'll get it as a ripple quantity. There is another formula like that. Lot of relations will get it simply by waveform. This is a current waveform, no, rising the current and then dropping the current. Rising case during on, dropping case during off. Similarly, I want I minimum and I maximum case, this ripple half of that. So total IL plus half of the ripple current. Similarly, IL minus half of the ripple current, that will give as a IL minimum. This will give as a IL maximum. Similarly, the switching average current and then RMS current, all these things. Switch current is nothing but a source current. No? When switch is on, only we are drawn current from the source. When we are getting the source current, whenever it is on. So on period duration 0 to T on. T on is nothing but a DTS. So that's why we'll get it as a I switch current D times of the average load current. So that is a inductor current. Now another RMS current. Only thing is same formula only, whole power 1 by 2. This is the switch or a chopper. Same thing, diode if I want. What you will do? This limits will change to off duration. What is off? 1 minus D into TS. So you can use that. We'll get it as a diode. Now you can see that instead of chopper, if I want to find what is average and RMS of the diode current, the diode of duration is a 1 minus D into TS. If we just integrate, we will get it as a the relations between the average diode current. This is a RMS diode current. Previous one is a average switch current, RMS switch current, like that. And similarly, ripple, capacitor voltage ripple also. Earlier we seen the current ripple. Now you can find the voltage ripple also. That is a delta VC. Delta IL is already calculated. This is a current ripple. This is a voltage ripple. Now you can see Q is equal to CV, or delta Q is equal to C into delta V. From that, delta V is equal to delta Q by C. Again same, no, delta Q is the area under which. So that area half into base into height. Use this formula. Then we'll get it as a Q, delta Q, and substitute here, we'll get it as a delta VC. So finally, we'll get it delta VC is equal to, this is a simplification. So just once if you know the delta Q and this value, you can substitute here, we'll get it as a delta VC is equal to this formula. And similarly, we'll see that boost converter. What else the boost converter different? These components are replaced. Again, same phenomena. Switch is on. What is only these two parameters will change. This is sufficient. If you have analyzed, still you can use the lot more waveforms also. Anyhow, I will show that waveform. Otherwise, this is also sufficient. Simple logic. Our derivation purpose, this small logic is sufficient. When switch is on, see that switch is on. What is voltage across the inductor? Same as input. And switch is off. This is open. Then what is the voltage across the inductor? This is middle between the source and load. That's why source minus output will give as a voltage across the inductor. Exactly same fashion, you can apply volt second balance equation and then current second balance equation or ampere second balance equation. You will get it as a derivation part. So now you can see that this is sufficient. If you want, you can analyze inductor voltage during on this magnitude, during off this magnitude. Current will be rises gradually, then decreases like this. This is a source current. Source current is nothing but whenever chopper is on, we can take it as a source current. This is a source current, and chopper is off, you are not taken from the source, like that. So you just this is this and this also same. Anything you can use it, but I used many number of parameters to represent. And now we can see that when the switch is on, what is the equivalent circuit? Because here what will happen, inductor is going to be store the energy, and for that what will happen, switch is on, all the current flows through the switch only, and that switching frequency I can write 1 by F. Similarly, you apply KVL notation, will get as a mathematical expressions. Now you can see that KVL, if I use, what is the input is equal to inductor voltage only, because both are same. VD or Vin or Vs, anything is same, don't confuse anywhere. Vin, that is equal to inductor voltage. What is inductor voltage? LdI by dt, that is equal to Vn, and from thus di by dt is equal to Vn by L, that is the switch is on condition. So del di by dt that is equal to V in by L. Same fashion, from that what I can write, when di by dt switch is closed or switch is on, what I can write from this? I want di by dt, this one, that is equal to what I can write, V in by L into delta t, this one. So as you know that delta IL by dt, that is equal to V in by L. From this, delta IL is equal to V in by L into dt. This is the one equation. Same delta I you can find when switch is off state. This is switch is on, close, on means close, switch is off means open. Under that condition you find delta IL under open. Both are delta IL, equate it, you will get the relation, simple relation you can see now. Other condition, switch is open. If switch is open, what will happen? Current is passing through this. Then what is the inductor value? You can see that same thing. If you apply the KVL and VL is equal to, you can write when the switch is off state. So now V in is equal to this plus this. Then I can write inductor voltage is equal to input minus output. Then L will come to denominator. Again we will get it as a, what is the delta IL, that is equal to V in minus V out by L into 1 minus D into T. This is the delta IL when it is open. Now equate. This is equal to delta IL when it is closed, and we will get what is the V out is equal to in terms of the V in divided by 1 minus D. This will get it. I will show that also. Now we can see I am equating both the same. I will show that this is the closed when the switch is open, V in minus V out by L into 1 minus D into T. That only I wrote here. And now equate it both. Why you have to equate it? I told no, it is under steady state condition, net change of the inductor current over one full cycle is equal to 0. So during on period plus during off period, that sum is equal to 0, and finally you will get it as a V out is equal to V in into 1 by 1 minus D. This is a boost converter. And similarly, we can see that during on condition, inductor current rises linearly because I1 to I2 or I minimum to I maximum. Under that condition, VD is equal to L into delta I. I2 minus I1 difference. No, when the current rises, I will show the waveform. Here current is rising like this. This is I1, there is I2, or I min, I max. So then the difference is what? I2 minus I1, that is equal to, I can write delta I, that is a difference. So that only I represented. So VDC L into di by T on, from this T on is equal to, we got it this, and then delta I is equal to under on condition. Similarly, under off condition, what is the off condition? Voltage V in minus V out is equal to minus n L into di by off time is T off. T off I can write, what I can write here, because total time T on plus T off. So therefore T off is equal to, this is the case, from that also we get it as a delta I, and this delta I both is same, and equate it, we will get it as a L value. That's all, simple logic. So now we will get L is equal to, also you can write, and then V out is equal to, this is another way of deriving the V out is equal to VDC into 1 minus del. What I did is, either you can get T on is equal to something, and from the delta I, and here also off duration delta I, equated these two, will get it as a V out is equal to VDC by 1 minus delta. Here also I done the same thing. See that V out is equal to VDC into 1 by 1 minus D. This way also you can do, or this way also you can do. Anything one is sufficient, no need to use both in exam. Now, so this is the relation, and now we use T on is equal, T on plus T off is equal to T. T on plus T off is equal to T. As you know that previous equation, this is the T on, L into delta I by VDC, T off is L into delta I by V out minus VDC, and from that L will get it. This is the L value. Same thing, T is equal to T on plus T off. So you know T on value and you know T off value, and simplify that, finally we'll get it as a L. What is delta I? that previous equation, any one of the equation you can use as a delta or I2 minus I1 if you know the currents. And then you can see that power input is equal to output, you will get the current relation. Here also same thing, IS input is equal to output by 1 minus delta, whereas here voltage side what we got, V out by Vn is equal to 1 by 1 minus delta. Instead of D there, here we will get 1 by 1 minus D. That is the relation. Here also transformer action is going to takes place. That is a DC transformer. When device is on, capacitor supplies the load current. And similarly, you can find what is the peak. Delta Vc is equal to 1 by C integral 0 to T on into IC. Just integrate this portion and then we'll get it as a delta Vc is a ripple, capacitor voltage ripple, and from that we'll get it as C is equal to only the just simplifications. I made it the substitutions also. Instead of giving direct steps, I given V out expression. This delta expression is like this from this equation, and the delta you can substitute here. See that delta or D are same. As in conventional previous we used delta, no, that's why somewhere I used delta also. D and delta are same, and you got it as a capacitor value and you got as inductor value. This portion is only for what you call it as simplification. Just I made it some simplification in this side, and finally you'll get it as a C value is this one. Now same thing buck boost, what will happen? You'll get it as a negative output voltage if you use as a buck boost converter, because there is a diode in the opposite direction. That is only the reason. So buck and boost converter can be obtained by cascading connection of the two basic converter. What are the two basic converters? Step down as well as the step up. You are cascading the two things, you will form as a buck boost converter. Either this converter will give the below the source voltage or above the source voltage. In a steady state input output voltage relations, we can see that there is a V out, because cascading I told, no. Once you know that one relation is V out is equal to Vd into D. This is a buck. Another one is V out is equal to Vd into 1 by 1 minus D. This is a boost. You cascade these two things. What I can get? V out is equal to Vd into D by 1 minus D. That is only the relation. We'll get it V out by Vd. D by 1 minus D. So the V out by Vd. Now based on the D is 0 to 0.5. You will get it as a buck chopper, and D is equal to 0.5 to 1. That will give as a boost chopper. So this is the relation. Now we'll see that circuit also same thing. Because of this diode, you will get it as a negative current. Again same logic. When switch is on and when switch is off condition. So when switch is on, let us assume that. What will happen? Switch is on, inductor will store the energy, then inductor voltage same as the source voltage, and then switch is off. This is also sufficient. You see that source voltage. When switch is off, inductor voltage only the load voltage. But the polarities, while it is charging, this is a plus and minus. No, while it is discharging, you get minus and plus. Then only diode is going to be forward bias. And that is the reason we'll get it as a minus V out. As usual, remaining everything is same. Only wherever the earlier notation, the voltage across the inductor, that is replaced by these values, automatically will get the relations. Now the input voltage source is connected as a solid state device. That is a second switch is a diode. That's what I told. No, all the cases, one is a switch, solid state switch, another one is ordinary diode we are using. Now the diode is connected in the reverse direction. That's why you are getting as a negative voltage also. Either this circuit you can use it, or otherwise simply this is sufficient. Because in the DC case, these waveform shapes are not uniform. That is what you have to analyze the circuit. When the switch is on, what will happen? Switch is off, what will happen? What is the current variation and what is the diode variations, and then ripple magnitudes. Let assume our assumption is a load current is constant. That's why I made it as a constant current. So that's the reason only this waveforms are sufficient for your analysis purpose. Now we can see again, when the switch is on, what will happen? It will store the energy. and that's what inductor store the energy during on condition, and switch is off, the polarity of the inductor will reverse and diode is going to be forward bias and will get it as a back to that of the source. This way we are connected to the diode and diode will be forward bias. And KVL you can apply and we'll get it, input is equal to the inductor voltage is same as input, and LdI by dt again same notation, this and boost chopper up to this is same, V in by L. From this delta I is equal to, I can write V in by L into dt, that is delta IL is a switch is closed. Same fashion, switch is open you can do and equate it, we'll get it as a relation V out by V in relation. Or else otherwise also you can find the delta IL notation under on condition, or T on and T off, you can do that, and then from that we'll get it as a same relation V out by V in, or T is equal to T on plus T off also you can do, we'll get the current relations. You can see that this is a when switch is closed, V in by L into delta T. Similarly switch is open, I will show here, switch is open, V out, so that is equal to V out by L. Now equate both. So one time period case, if we equate it, this is as usual, open case V out by L into 1 minus D into T, and you can see that one time interval open plus close both sum is equal to 0, we'll get it as a V out by Vn. So this minus sign represent, you will get it as a negative voltage in the output. Wherever if you required minus 5 volts or minus 10 volts like that, you can in our projects and all some FPGA and all you may be required plus 5 volts, minus 5 volts like that for the input supply. At those conditions you can use as a buck boost chopper also. And similarly, as I told, greater than 0.5 we'll get it as a buck boost chopper, and less than 0.5 it is a buck chopper. So that is the variations. And similarly you can see that same, once if you know one derivation, only the values is going to be changed. Input is equal to L di by dt, that is a delta I2 minus I1. From that delta I is equal to this. This is not required anyhow, previously we got it V out by V in notation. Here also same relation will get it. If I equate these two again, you'll get this. That's why 2 times I done it. Any one you can is sufficient. Similarly, T is equal to T on plus T off, you sum it, we'll get it as a L value. And similarly, you'll get the capacitor. So this input is equal to output, we'll get the current relations. Again transformer action only, but only thing is instead of K, you will get it as a D by 1 minus D. And another one capacitor. So delta VC 0 to T on integrated, we'll get the capacitor value. So this is the all the relations. Only thing is when you are doing the problems, you require these relations. Just practice once. Any buck or boost or any one, only replacement. There the voltage across the inductor VDC, that may be replaced by the V in minus V out like that. That changes only, we made it, all other things are same. So this is the end of the half of the unit that we call it as a choppers. The next in the same another half we have as a cycloconverters as well as the AC voltage controllers, but these problems are left out. We'll see after that theory part, all the problems we'll solve it. Buck boost chopper, buck chopper, boost chopper, buck boost, and then a cycloconverter, AC voltage controller problems. We'll see that in the next class. If you have any doubt, you can ask me. And from the maybe next class is a physical class. When I'm solving the problems, you bring the calculators. After completion of cycloconverter and then AC voltage controller only, we'll solve the problems. If you have any doubt, you ask me. Otherwise, you can leave.